The Billard ball is shot east at 2.28 meters per second. A second identical Billard ball is shot west at 1.33 meters per second. The balls have a glancing collision, not a head-on collision, deflecting the second ball by 90 degrees and sending it north at 1.74 meters per second.
First ball is going 2.26 and the other one's 1.23. Okay.
Also, it's 2.28.
Oh, 2.28. So momentum problems, the best thing to do is just draw like a before and after pictures. So this is before they hit. And what happens after they hit?
The balls have a glancing collision, not a head-on collision, deflecting the second ball by 90 degrees and sending it north.
So ball B is now going straight north.
At 1.74 meters per second.
Okay. And what do you think ball A is doing?
When it hits.
Yeah, right after they hit, because they kind of hit. They're coming towards each other and they glance off of each other, and ball B goes straight up, and ball A goes somewhere else.
It's like kind of like southeast-ish.
Yeah, it'd probably start kind of going like that,
Yeah.
some velocity. We don't know. That's what it's trying to figure out. Okay.
So that's for the speed of the first ball after a collision. So,
So this is conservation of momentum.
okay.
So what do we know about this and this? Like, what are their momentums going to be? Or how are they compared to each other?
That's interesting. Ball B is going faster than it was before.
Yeah.
Ball A is, well, I guess we don't know. The momentum, do we know the mass of the balls?
No, we know they're identical. They're the same mass.
Okay.
So we'll just call it all M. But it's conservation of momentum, right?
Oh,
So any momentum we had before, this is our P initial, it's going to be equal to any momentum that we have after, right?
right.
So that's how we solve all these problems. Is you know that the momentum before is going to be equal to the momentum after. Before it's all in a straight line, but after it's what happens.
Different directions.
Yeah. So how do you think we deal with different directions in momentum?
Find the angle. They're going.
Right. And then you can break it down. Do you remember when we did like,
X and Y coordinates or whatever.
yeah, so you break it down into components. Okay. So taking into account both of these, what is the momentum before?
it's gonna be bigger than the MB.
Well, the masses themselves are the same,
Right.
but the momentum will be bigger, yeah.
Yeah.
So what's the momentum of A?
Guess you just do 2.28.
Right, you have to put the mass in there, but it's just an M.
Yeah.
So it'd be M times 2.28. Then what's the momentum of B?
Mass times 1.33.
And then since they're both on the x-axis, how are we going to combine the two of them?
Cosine.
Well, without using, you don't need to use trig, they're both on the x. But will one of them be negative or positive?
Oh, yeah. 1.33 would be negative.
Right. Okay. So your initial is going to be 2.28 minus 1.33. So that's like 0.95 maybe? No. Yeah, 0.95. Okay. So that's your initial momentum. What's your final momentum going to be? This is initial in x, right? What's our initial, what's our initial in y?
What are the ones after now? Or is
No,
it-
just before.
Oh, okay.
Is there any momentum in the y direction?
Zero.
Okay. So that means that our final in x has to be equal to our initial in x. So it has to be m times 0.95. And our final in y has to be the same as our initial in y, so it has to be 0.
Okay.
So what are the equations for our momentum in x? For the final momentum in x.
Data 1.3. Cosine theta, or
Well, no, you just want to look at these two right here.
okay. So we're looking for the x coordinates or the x components.
Yeah.
And A is the only one that has an x component.
Okay. So that would be what?
Would you do mass times, is it negative 1.33? No, A's 2.28.
Right, but the velocity has changed. Just like B's velocity changed, A's velocity will change.
Oh, right.
So you don't. All you can do is say MVA times the cosine of some angle, right?
Yeah.
What does that equal to?
Zero?
If it was the y, it'd be equal to 0.
Oh, it would equal to m times 0.95.
Okay. And then what about our y direction?
It'd be m times 1.74.
Okay.
Times sine.
Minus m VA sine.
Sine.
And that's all equal to 0.
0.
Alright. So the best thing about this is the masses all just cancel when you go to solve it. So then we have velocity of A cosine of theta equals 0.95. And then we have, add this to the side, 1.74 equals velocity in A sine of theta. So you have two equations with two unknowns.
Right.
So I would solve one of them for velocity A. So I'd say velocity A equals 0.95 over the cosine of theta. And you plug that in over here, so you have 1.74 equals 0.95 over the cosine of theta.
Times sine.
Yeah. This is the tangent, sine over cosine.
Oh, yeah, that's right.
So if you divide that out, then you can use the inverse tangent to find it. So is your calculating range, I know.
It's in degrees.
Oh, when you did, let's see. Yeah, that would be the tangent of the angle, right? So you take the inverse tangent of that answer.
Oh, that's right. To do 1.74 divided by 0.95.
Yeah.
Inverse tangent.
Yeah, so
So it's 0.95 divided by 1.74.
no. So your answer right here, you take that and you take the inverse tangent of that answer.
Right, okay. $61.366.
Okay. So this is 61.366 degrees. And then we can plug it in here, right? So velocity of A will be equal to 0.95 with the cosine of that angle.